Hey everyone, welcome. I was told that this slot is special because there's like 4 or 5 really interesting talks at the same time. So I'm surprised and happy that you made the choice to be here. I hope I can give you enough information that ensures that the time you're spending here is actually valuable for you. So I'm Vishnu. I've been working on Kubernetes ever since the project started. Uh, since the beginning, I've been focusing mostly on like the node and like resource management and like how does scheduling work and like how does the system look like overall together. More recently, I've been trying to focus on enabling machine learning at a like an overall system stack level and making sure that all the pieces fall together such that the end user experience makes sense. So I'm not here to talk about that specific effort. I'm here to talk about how the resource management working group is functioning within the Kubernetes community. What is it trying to do? Who are we, and like what's our agenda, and what have we accomplished so far, and so on. So scope, and they have abstractions, and they can go and maintain it and have a process around that piece of module. So whereas a working group is doing the opposite, which is like I have a specific problem to solve within a SIG, or I have problems improve compute resource management, because it was something that was partially being tackled before the working group was formed. What we were mostly focusing on was like, how do we get the system to be reliable? How do we get the node to be really reliable such that things don't fall over, right? We're only focusing on reliability. We're not focusing on anything else or any other features and functionalities. So I think last year or maybe the year before KubeCon in Seattle, we decided that, okay, we need to start spending some time on adding functionality and adding features such that we can support more workloads, more applications, and also like improve the experience of existing supported workloads in addition to just reliability. So our first task was literally to go ahead and like figure out a roadmap and see how we can start executing and what the priorities are and so on. So that's how the working group was formed, and we're currently spending most of our energy tackling compute resource related topics across the system, like across scheduling, monitoring, nodes, and then like even the API machinery and so on. Like how do we get the whole system to behave really well? So I also want to talk about the community because I'm a representative here, but there's so many other people who are actually actively contributing as I speak. So it's a really active, big community, and we are all like genuinely surprised at the sheer amount of interest in this specific area, even though it's a sub area. So there's more than 30 plus active contributors. In addition to that, there's like so many other people who show up and give their opinions and feedback. And there's lots of diverse use cases and users that are being represented, ranging all the way from like Raspberry Pis to like those high-end NVIDIA servers, which have like really interesting scenarios. And then like we're sort of like tackling really hard problems where we don't have examples to look at. Like we don't like for Googlers, we always look at Borg, and we think, oh, we've done it this way in Borg. Should we just do the same thing or should we adapt? But some of the problems we're tackling here have not been solved in Borg, and so we don't have a different system to look at and draw a parallel. So sometimes like that's the reason why I wanted to highlight that some of the problems are really hard. If you're interested, I can mention a few of them after the talk. And we meet bi-weekly over Zoom, and then our in-person meetings are approximately once a year. I also want to show a picture from a recent in-person meeting that we had. We met at NVIDIA, who hosted our most recent meeting, and there's about like 40 people who showed up, and we actually had 2-day-long sessions. And so this is just to highlight that there's an active community behind this. Let's keep going. So what are some of our past accomplishments? So we spent quite some time on compute resource extensibility. So the way Kubernetes was maybe 6 months back is a situation where if you want to introduce any new resource, you have to go change lots of code components. And for those of you here who have tried or attempted to add new features into core, you know like how rigorous it is and how difficult it is, because Kubernetes wants to make sure it's portable and it's scalable across a variety of environments. So it's like a really high bar to add something into the core. So we started focusing a lot on extensibility, where in order to like implement a new concept or a new feature, let's say we're adding support for a new device, we don't have to go and change the core completely. So we decided that extensibility is a really important thing that we have to focus on. And so we spend a great deal of energy getting extensibility to work, and also not just work in a sense that we demo that it works, but also have production systems that are running through these extensions. So some of the key elements that were added was we introduced this new concept called device plugins, which is currently beta. So we have GPUs that are supported through device plugins, and that interface is running in production now. And so we have quite a bit of runway with that interface, but it's beta because there's so many other use cases that it does not support yet. I'm going to be talking a little bit more about those use cases in detail, but just to give you an idea, like we cannot support network devices now, nor storage devices, nor can we support devices that have to be passed through to a VM guest, for example. So there's still a long way for us to go there, but we have something that's meeting users' needs today. And we also made some changes to scheduler extensions such that you can now introduce like your own node level or cluster level resources without again changing the system. You can literally like drop in an extension point, which would then go plug in to the scheduler, so you don't have to write a new scheduler. At the same time, you can also extend the node with device plugin. So you got this secondary system within Kubernetes where you can add your own custom logic without having to change the core or fork the core. We did some work on CPU scheduling. Our focus here was to like get rid of CFS for apps that are really, really latency sensitive. So how can we just put them on a core and not worry about those apps ever getting in trouble because of CFS? So we started with we had a grand goal of like saying, okay, we'll do this automatically. So we'll figure out like what is the performance of a given process or given set of processes. We'll observe its CPI, and then we'll automatically tune everything. But that seemed like a multi-year effort. So we said, okay, we'll first start with just static pinning, where if a pod shows up where it's asking for integral number of cores, then we'll just give it a single core or like whatever number of cores it asked, and that's it. It's statically done. If there's fragmentation, then we just deal with it, and that's a state of the world. But then we also have our ambitious goals that I mentioned earlier, which is not making it available just for integral cores, but also for other use cases such that the user doesn't have to worry about fine-tuning CFS or fine-tuning Quota and so on. It's like it just works, and we can present to the user what sort of latencies they can expect, like what sort of tail latencies the system can guarantee, and then design the system around that. So that's something that we look forward to doing in the future. But what we have now is just static CPU pinning. We also added support for huge pages, which again is very useful for quite a few applications, which again suffer from the regular page allocation latencies. These features are very, very important for really latency sensitive apps, but for the regular ones, maybe you don't care. It's like your app is functioning better than what it used to, so you're happy already. But then as you keep going, as you try to improve your efficiency and utilization, maybe like 2 years from now, all these features will start mattering quite a bit. So another thing that I want to highlight is like whatever I described here, we literally achieved this in like 8 months. As the Kubernetes project was growing, the number of contributors was increasing. We've been having quite some difficulty in scaling people and like scaling communication. And so that's the reason why I want to highlight this, in that like, even though we have a large community, we are able to execute together, and we have been able to ship features together. And it's also close collaboration across SIGs, because a few of us in this working group, since we have been with the community for a while, we're able to like interface with many other SIGs and make sure that we get participation across different SIGs. So what are some of the future projects? So we want to continue with compute resource extensibility. We want to make the API really feature rich, such that you don't again have to change the core. You have to literally like write 0 lines of code in order to introduce a new resource into the system. But on top of that, we also want to support a few more concepts like, as a developer, I want like higher level primitives than lower level primitives. To give you an example, let's say having a bunch of different network devices, or I have different kinds of GPUs or different kinds of CPUs. All I care about is if my application has dependency on certain instruction sets or certain properties of the devices that it wants to run on. As a developer, I only care about those properties. I don't care about which exact device I'm running on, because my app is portable in theory, so I can take it and run it anywhere, and I can share my app across different users. But if I'm writing my app against a very specific set of resources, then it's no longer portable, and the whole Kubernetes promise is like out the door. So we want to bring a balance between, on one hand, like we have to deal with the reality of like architectural diversity. On the other hand, we also want to have separation of concerns. So how do we bring forth such a system where users can, as a developer, I can just describe my higher level needs, and the system can translate that into lower level actual concrete resources. So that's one of the key pieces we want to enable. There's been some active work going on here defining APIs that are again extensible and can also be expressive enough where users can say, hey, I want a device with so much memory which supports, say, AVX2, for example, and then we'll figure out what's the right set of nodes to schedule those pods on. And then we also want to improve the extensions at the scheduler level and at the node level. Like I said earlier, there are more use cases that we are not able to support, and there's also like usability issues that we want to address. And then we also want to support cluster level resources. There's no such concept now where with the scheduler extender, you can like add a cluster level resource, but it's still the amount of maintenance and the amount of development necessary to introduce a simple resource is quite high. So we want to change that. So we want to make it like really easy where you can inject a cluster level resource and the system knows how to deal with that. And we also want to support network devices. This is like a really hotly discussed topic because network devices, they're both network and devices, and so they span multiple abstractions. And so they're a little bit tricky as to how we're going to abstract them, in that like they're not just a resource, but they also bring along some other baggage which the networking industry has carried for so long. So it's like, where do you draw the line, and like how do you expose it to the end user? So another project that we're working on is like hardware topology awareness. Again, this is something that traditionally people have fine-tuned manually, where you fine-tune an app to run on a specific NUMA node or a specific set of CPUs, and you choose the right GPU you want to run on, and like so on and so forth, right? Like if you have a network app, you choose that I want to run on CPU socket 0, for example. We don't want users to do that. Like we just want them to choose an SLO band or like an application priority band, and the system would automatically place them on the right set of nodes with the right set of properties, and like keep fine-tuning that over time. So this was something that at least Google was able to accomplish with Borg, and we had like quite some success with that. So we want to like bring forth again that set of feature functionalities into Kubernetes. Again, but we are also dealing with newer age hardware that we haven't seen so far, especially in the ML world, where a lot of the general purpose hardware are going away, and then special purpose hardwares are showing up almost like every month. And so they have their own set of requirements and own set of constraints. So we're trying to model Kubernetes such that it can, again, like fit different needs, ranging from Raspberry Pis to the high-end machines. We want to support cluster level and node level scheduling, in the sense that we want the nodes to optimize as much as possible. So as a developer, I don't have to care about how is my application performing, because I know for a fact that I'm going to get certain level of tail latencies because the system has been benchmarked and the system has been set up such that it can guarantee that. But at the same time, I also want to improve utilization, and I don't want to have too much of fragmentation. So then you might want to take a higher level and like look at all the nodes and do scheduling a little bit more smartly. So we want to empower that use case as well. And we also want to have like performance tracking such that we can make sure we don't get regressions. At the same time, we can also like keep fine-tuning the system and identify bugs in the system as it's functioning. And monitoring is another hot topic. Like Kubernetes is adding lots of extensions because it cannot scale to meet varied use cases ranging from different vendors and different users. We're focusing a lot on extensibility, but we don't have a good extensibility story for monitoring and logging today. So this working group is trying to help the monitoring part a bit by figuring out how do we decouple kubelet from the data plane for collecting metrics. So you can literally like drop in a plugin that's been given to you by a vendor, and monitoring just works with Prometheus. So you don't have to change anything in the code. So we want to work towards that kind of a user story, and that's part of the effort. We also want to do application performance benchmarking. Right now, we don't measure anything. We don't measure performance at all, and that's not a good place for Kubernetes as a project to be in. So as a community, we're also investing in developing black box measurements to inform us like how are different popular applications performing, like how is Memcached performing, how is JVM performing across like most common environments. And we want to like track those metrics, make it available publicly so we can track it across releases and across feature changes. Actually, that's all the content that I had. I really didn't want it to be just a download from me. I wanted this session to be more interactive. So I would love if you have any questions and if I can answer them. Go ahead. Okay, so the question is, what's the state of the art? And you were trying to be a little bit more specific with GPUs, right? Okay, because that might help, because otherwise the space is too large. So when it comes to GPUs, we actually have a few production systems, like I said earlier, that are using the extensions that I just mentioned, like device plugins and scheduler extensions, in order to make GPUs compatible in Kubernetes and actually function in a production-ready manner. Correct. You don't have to make any change to source code, and then you can deploy your drivers and your plugins as like one bundle, and then you can maintain that bundle through your regular node maintenance process. So it's like hot plugging into the Kubernetes system. The question is, are there other resources that have the same support now? So we had proof of concept for a Solarflare NIC. I think some of the folks from Intel are working on FPGAs. There's a gentleman there who can talk a lot more about FPGA support. And we've seen a few other device plugins in the wild. Like, we get links for them, but given that they are an extension, there's no need for developers to come back to the community and say how they are consuming it. So we're not like, all that information is not available to us, but I think it's an early stage. Like it's been just 6 months, and it's been like 3 months since we went beta. I think this is when people are ready to start taking the APIs because they know they don't have to change it every 3 months. And so I would expect more and more devices to show up in the next 6 months to a year. Yeah. Question? Okay, so the question is this the right place for rescheduling, or is this the right discussion point for rescheduling? It is and it is not, in that like some part of rescheduling is just literally a cluster level daemon that you're running. And so from a Kubernetes point of view, there is no explicit rescheduling of pods. You just create a new pod, right? Once a pod is bound to a node and started there, it's going to be there. There's no moving of that pod. So literally deleting that pod and creating a new one, right? So from that point of view, you can write your own controller that does that. But when it comes to how do I expose a new resource after a node is up and running, we have the technology to do that already. So the device plugins is the thing that you might want to look at, where you can literally hot plug a device in, and then it can detect that a new resource showed up, and then now it's going to be in your system. And then if you have a pod that's requesting that resource, then scheduler will automatically place it on that node. Did that answer your question? Yes or no? Yeah, definitely. Yeah, definitely. I would love to hear more about your specific use case and what the gaps are right now. Okay. Okay, the question was, do we still need QoS classes given that priority is in place? So that's a little bit tricky in that like QoS classes were originally meant to guarantee performance, although we did not start executing on that. Priority is just to make sure that the right set of pods are running on a system, especially when you have like batch-like scenarios where you want to load the system as much as possible so you can do cycle stealing. But at the same time, when you have an important workload that you want to schedule against the system, that workload runs. Like you have a paper deadline versus like you have this 1 year long project, and you want to be able to differentiate between the two. So priority is more geared towards that. But in the node level, it gets a little difficult because from a user point of view, it's very easy for you to think in terms of priority, whereas when it comes to QoS classes, it does not represent priority, right? Like you don't have multiple levels there. You just have only like 3 levels with QoS classes. So you can't map the notion of like an intern and like a researcher who has a deadline tomorrow into QoS classes. So priority is what is mainly taken into account when it comes to evictions, primarily because of that reason, because we want to evict the pods that are not important and make sure the pods that have to run will run. But when it comes to, so that's the preemption part, but when it comes to evictions, we took priority into account because if we, like one option that we discussed was we'll never disturb any guaranteed pods because they have been guaranteed some resources and they're not exceeding that. And then we'll only go after any pods that are exceeding their requests. But the feedback we got from the community was that I can run a guaranteed pod, like an intern can run a guaranteed pod, but that doesn't mean that pod has to continue running, right? Like I have a really more important pod which might want to use more resources, but it's important and I have like consciously made a choice to make it important. So in that sense, we want to make sure that if you're running like say a system critical pod, like so you're monitoring add-ons, for example, and they happen to exceed their requests a bit, we don't want to like punish them just because of that. And if we can evict a lower priority pod, that might actually be better from a system reliability standpoint. So that's a fine line there. So my short answer to you is we still need QoS classes because we want to represent performance SLOs in the future. So that's not going to go away anywhere. But the combination of QoS and priority classes is a little bit tricky. So my understanding, I hope I'm not wrong, is that we take into account both, that we order by priority first, and then we go by QoS classes. If there is no guaranteeing of class, I would probably consider that a bug. because you don't want to, once you choose a priority class, you don't want to go and evict pods, like say evict guaranteed pods there, because maybe you have like a best effort pod that you want to evict first. Okay. Yeah, which still respects classes. Okay. Yeah, the way the quas classes are not an explicit concept in the API. They're derived from the way requests and limits are specified. So that derivation is still in the system. So from that point of view, you would still see quas classes, but how are they actually put into use today? They're not put into much use, and that's what we are working on with this working group, which is to actually start stamping SLOs for different resources. Yeah. Okay. Question? Okay. Yeah, the question is, how is CPU scheduling expected to evolve, especially CPU quota, because it's causing pain today. So CPU quota is not something we originally wanted to add. I think there were like a few use cases which sort of forced us to add in the past. So it's still a feature you can opt out of. Like you can run nodes where you can turn off that feature, but like most major clouds or managed distributions of Kubernetes are actually like turning it on by default. So there's an active discussion about this in a GitHub issue. So my opinion on that is that I would prefer disabling CPU quota by default because I really don't see much use for it. It's helpful when you want to do like power capping mostly, or if you're running like really compute intensive tasks and you want to make sure like they don't cause issues in the CFS for rest of the tasks, like you're running transcoding or something that's really compute intensive and trashing the cache, for example. But we haven't seen many use cases for that, and most people are running like web applications with Kubernetes, and so having this Quota kick in and then take off the process for quite a while is going to result in like a spiky pattern, which is probably not ideal. So my suggestion so far in the community is to disable that by default and only enforce it for burstable and best effort pods. And that way, the guaranteed pods don't actually get penalized, and you actually have more reasons to run guaranteed. Like you would get static CPU pinning if you choose integral cores. And then in the future, we can be a little bit more serious, where we can isolate guaranteed pods away from like best effort and burstable pods, such that they get like more better guarantees from a CPU standpoint. Like the expectation there is like users would run say cache thrashing pods as best effort, and it's mostly batch. But if people are running batch as guaranteed, then that's not going to work that well. But that would be the direction I would try to convince the community to move towards. Do you have any specific opinions or thoughts on that? Correct. You can disable CPU quota, but it's not per class. It's for the whole system, for the whole node. So you would disable CPU quota by default. Well, I mean, the statement was, what if we have compute intensive and latency sensitive tasks running together? So we're expecting CFS to function pretty well, but if you're hitting issues with CFS itself, either like you should go fix the Linux kernel, or we should, or what you could do today is like you can set integral core limits for your compute-intensive tasks. That way they're pinned to CPU cores. Or in the future, when we are actually able to detect application performance, we might be able to isolate them onto different sockets or different cores. So we haven't gotten to that future. That's where we want to get to, where we can observe application performance patterns, and we can observe which apps are victimizing what apps, and so we can isolate them from a system point of view rather than having the users manually tune all of this. Right. Sure. The next statement was like, what do we do with tuning CPU quota period? The reason why it's not exposed is because it's most likely a per application property and not a per node property, because the node is being shared, just like you said, with different applications. And so then that means you have to expose it through the API. And that's exactly the wrong direction we want to go in, because we want to do all of this within the system, right? Because we don't want every user to care about every single property of the environment that they're running in. Then the value of Kubernetes is lost. Like literally, compute resource management was one of the pillars when Kubernetes project was started, right? And so we want to make sure we can deliver on that pillar and not expose all of it and make it like an HPC system. So that value there is then lost. So that's the reason why it's not exposed today. But we could consider adding a way to override it, but I would much rather prefer turning it off. Like if you have a real use case for it, a real need for it, then I would love to hear your feedback. And maybe if you can post your thoughts on the issue too, I think it might benefit the rest of the folks who are passionately commenting about it. Okay. Question. Mm-hmm. So the question was, what about storage and storage devices specifically, and how are they going to be exposed? Storage is not currently in our radar because there's like a complete different set of storage APIs, especially with the introduction of CSI. There's a lot more flexibility when it comes to storage. But then when it comes to new age storage devices like PCI, NVMe devices, then they fall into the same bucket as the rest of the things that we're dealing with. And so we have to figure out how is the interface going to look like, whether it's going to be a storage interface which is primarily file system based, but there's also some block device support being added, but there's no understanding of like hardware topology and so on. Whereas on the other hand, if you had a local SSD, for example, you could just expose it as a block device, and in theory, like the existing device plugin API could be extended to do that. But that's an area we haven't actively explored yet because we haven't seen requests for it yet. Like if that becomes a priority for users, then we'll be able to like prioritize that and deal with that. But there are solutions possible. It's just we have to figure out the right one. Question. Okay, the question was, would it make sense to have a single unified extension point across all different kinds of devices like storage, network, and compute? That's again, I think there's some history behind it in that not all storage devices care about like topology. Maybe not all network devices care about it. So I think the new age high performance computing applications, especially driven by like AI and ML, those are the ones that are pushing for all these requests to become important. But otherwise, there was no importance for convergence there. But at least from an operator point of view, Tim Hawken has been pushing quite a bit for unifying the way vendors are building extensions and how they are packaged, so that they can at least be deployed together, even though there are 3 different extension points. But when it comes to hardware topology awareness, I guess we'll have to start with compute first and then extend it to the rest of the resources. Okay. Are we out of time? Okay. I'm going to be out right next to the door. We're out of time, but if you have any questions, I'm happy to chat with you a little bit more. But thanks everyone for showing up. Hope you got something useful.